All right, well, welcome back. So now we turn from infinite sequences to infinite series. An infinite series is the sum of the terms of an infinite sequence. So, in other words, we add up all of the terms of the infinite sequence. So, on forever, or as we would write it, the sum as I goes from 1 to infinity of a sub I using our summation notation. This is called an infinite series. Now, my initial thought might be if you're adding up an infinite amount of things, isn't that just going to always be infinity? Well, it actually depends. It actually depends, as we're going to see. So let's consider a sequence here, and we're going to look at the different terms of that sequence, or the we're going to start to look at an infinite series with this sequence. So consider the sequence here. A sub n equals 1/2 raised to the nth power. Okay, so sequence A sub n looks like this. 1/2 to the first, 1/2 to the second, 1/2 to the third, 1/2 to the fourth, and so on and so on. Okay. So what we do is we consider to talk about the infinite series, adding all these terms up to infinity, we consider the partial sums. What we call partial sums. S sub n, which is equal to the sum of the first n terms of our sequence. In this case, the sum is I goes from 1 to n of 1/2 raised to the n. And so we define a new sequence, which is the sequence of this partial sums. And so then we have a new sequence, and we talk about, does that thing converge? Does that thing converge? Well, let's look at the first few sums of this sequence. So S1 would just involve the first term, which is just 1/2 to the first power, be 1/2. Okay. S2 would be 1/2 plus 1/2 squared, which would be 1/4. So that equals 3/4. And then S3 would be 1/2 plus 1/4 plus 1/8 will actually be 7/8. And then finally S4 would be 7/8 plus 1/16 is going to be 15/16. Okay, so we immediately start to notice a little bit of a pattern here. And we can kind of realize that pattern is going to keep continuing, because the next one would be 15/16 plus 1/32. And so this pattern continues on. And so what we notice first is the denominator. The denominator is literally just 2 to the n. Right? The denominator is literally just 2 to the n. The numerator is always 1 less than the denominator. So with that information in line, we can decide and actually generate a formula for Sn in this example, which is that it's 2 to the n minus 1 on top divided by 2 to the n. So we've now actually based on the patterns that we've observed and how these patterns will just keep continuing like that. The next one will be 31 over 32, and so on. We actually can generate a formula here for Sn in this example. And since we have a formula for the terms of a sequence now, we can talk about the limit of that sequence. So we can talk about the limit of that sequence by looking at the limit of the underlying function. Right? So we could say x, or actually we'll oftentimes here maybe even drop the x and even just use n, but I'll do it with x, as we've been talking about x as a variable and n being just integers. So limit as x goes to infinity of 2 to the x minus 1 over 2 to the x. And what we realize is that minus 1 really contributes nothing. So this is the limit as x goes to infinity of 2 to the x over 2 to the x, because the minus 1 is going to contribute nothing. And of course, those would just cancel out. And so this limit is actually just 1. So therefore, we would say the limit of the sequence to the partial sums is 1. So therefore, the infinite series, as I goes from 1 to infinity, of 1/2 raised to the I power. Just make sure oh, there's one little typo I just realized earlier. So that sum there is equal to 1. And I just realized I made a little typo earlier when I wrote that out. That's not 1/2 to the n. That should have been 1/2 to the I power. So the little typo on that. So I apologize for that little error there. That should have been 1/2 to the I, right? Because it's the formula for the an as I goes from 1 to n. That should have been 1/2 to the I. But we can see here that this infinite series is in fact just equal to 1. It converges to 1. And so we're going to talk a little more in the upcoming video about what it means for a sequence to converge. Okay.